Larson is the Senior Vice Chancellor and Provost of the State University of New York System. He joined SUNY in September of 2018. Before coming to SUNY, he was the president of the Khalifa University in Abu Dhabi, United Arab Emirates. He was the founding president and served its leader since 2010. And then prior to becoming president of the Khalifa University, he was a member of the faculty at the Duke University between years of 1992 and 2010, during which time he had an appointments in civil engineering, biomedical engineering, and mechanical engineering. And he served as the chair of the Department of Mechanical Engineering and Material Science from 2008 to 2010, and also served as Senior Associate Dean for Education in the Pratt School of Engineering from 2002 to 2008. And also he had oversight responsibility for all undergraduate and graduate engineering programs at Duke University. Professor Larson earned his PhD and master's degrees in mechanical engineering from Stanford University, and he specializes in computational mechanics in the subfield of engineering mechanics concerned with development of new computational algorithms and tools used by engineers. He has published over 100 refereed articles, book chapters, and abstracts, and has authored or co-authored 2 books. His particular focus is development of methods to analyze contact, impact, and frictional phenomena in highly nonlinear and complex systems. He is a fellow of the American Society of Mechanical Engineers, the International Association of Computational Mechanics, and the United States Association for Computational Mechanics. He also holds membership in the American Society for Engineering Education and Tau Beta Pi, and he served as an at-large member of the Executive Committee for the United States Association for Computational Mechanics between 2007 and 2010, and currently serves as a member of the Executive Council of the International Association for Computational Mechanics until 2020. And additionally, he has served on the scientific advisory committees of several of the most important national and international congresses in computational mechanics. Please welcome Professor Larson.
Thank you, Jamal. Good morning, everybody. It's really a pleasure to be here, and I was telling a small group of faculty, it's really a pleasure to be presenting a few slides with equations on them, because I don't get to somehow do this quite as often as I once did. We kind of went back and forth. We met at a faculty meeting a few weeks ago. Very kindly extended the invitation to give a lecture to you all today, and iterating a little bit on what I was going to talk about. And you mentioned the 2 books, and one in particular that's sort of a research monograph, things over the last 20, 25 years we've thought about in computational mechanics and for contact problems in particular. So in a way, the lecture I'm going to give today is going to sort of pick up where the book leaves off, in a way. And, you know, I think the overriding goal of our work, I'm a finite element person by background, in nonlinear continuum mechanics, I would say. And when I sort of entered this field as a graduate student, the situation we had, and I was working in the national laboratories at the time, the situation we had was we had fairly robust methods for things like computational plasticity, computational geomechanics, CAP models for concretes, the kinds of things that those of you who work in these media, I think, will recognize. We sort of knew, and they were coming out, I would say, in the 80s and mostly in the 80s and to a certain extent in the late 70s. These methods were pretty well standardized for finite elements and how to treat those sorts of problems. But for contact mechanics, the story was a little bit different. So you showed me nano-indenters, right, in your laboratory. So my first research project as a graduate student was funded by IBM. And it was sort of the early indentation studies that were done by IBM and folks at Oak Ridge and folks like this, having to do with characterization of the thin films that are put on disks, right? Both the magnetic media, but then the protective coatings that are put over those. And so So the question in those days, and I know there are people on your faculty who are still grappling with that question, is to what extent can we use continuum mechanics to describe things that are getting down to, let's say, 20 to 30 nanometers, something like this. So this was my challenge as a graduate student, to try to sort of use methods of continuum mechanics and computational mechanics to try to study these problems, but you can't get around contact, you can't get around friction. And so this was kind of my original foray, if you like, into thinking about this topic. That was the application that I had in mind, but I'll show you a few others, and keeping in mind that I spent quite a bit of time in mechanical engineering departments. Some of the applications I'm going to talk about are perhaps more mechanical than civil, but I think you get the idea physically the kinds of systems we'd like to simulate. So a few acknowledgments I need to do. I'm actually going to use some slides that were provided me by Abacus a few years ago for applications they like to sell using contact mechanics, and I think it gives you at least some kind of snapshot as to what the current state of the art is in this field. The mortar methods, which is really the meat of my talk today, several collaborators over a 10 or 15 year period, some of them graduate students, some of them collaborators in the national labs, Martin and Mike in particular. And then the other thing I'm going to talk just a little bit about is fluid structure interaction, and how some of the things that we thought about in doing contact mechanics, solid to solid or structure to structure, sort of have some interesting potential applications, at least for FSI. And so just to give you a little bit of an idea, again, from a numerical point of view, how one goes about doing that. So I've already said a lot of this, but so the idea here, keeping in mind that I'm sort of a methods developer, okay? The idea here is to sort of come up with tools. You can think of them hopefully as sort of being under the hood, not anything, if you're a user of a code like Abacus, you have to worry about too much. But what we were really after was use whatever friction model you want to use, whatever interface model you want to use, just like you employ a plasticity model or an elasticity model or an anisotropy model for a bulk solid. We'd like to give you the same sort of robustness if you have to describe contact interaction. But it's quite a bit different, right? And so I've got a sort of an embarrassingly old movie here, but if you sort of watch this thing go, so this is a tread block simulation we did for Michelin a few years ago. So finitely deforming, basically this is a Mooney-Rivlin solid, actually contacting the roadway, which you can't see here. It's just sort of taken as a rigid, transparent obstacle, right? That's actually the easy part of this problem. The harder part of the problem, and you can just sort of see some hint of it as this thing goes, is the contact that occurs inside the sipes and the grooves as this thing rolls. And these are the kinds of things that if you tend to run your tires too long, which I tend to do, you can actually see those wear patterns. And so the interest Michelin had was to actually model that and see if we couldn't get at the energy dissipation that was happening there. And again, you can think of your favorite application. You've got contact, you've got friction, you've got large deformations, you've got potentially large relative motions. And so we'd like to come up with methodologies that will work sort of without limitation on those things. And then we also, although I'm not going to talk about it a lot today, there's also some interesting things that come up when you're doing true dynamics, right? And you want to get transient phenomena. A lot of the same concerns come into play. So I'm going to sort of use, and I'll go through them pretty quickly, I'm going to sort of use this set of slides that my colleagues at Abacus gave me a few years ago, just to sort of give you some ideas from the sort of tire rolling industry. And again, you can visualize your favorite application, just to sort of give you an idea of some of the things people would like to do with these methods and what's now possible. So I showed you our silly sort of academic tire that we were sort of doing to demonstrate concepts for Michelin. But in fact, if you're using industrial software these days, you can do these things pretty much in real time. Abacus is pretty well connected with a lot of major tire manufacturers, and so People can look at two-dimensional, axisymmetric models. They can spin those, or they can develop full 3D models and literally roll those down the roadway. There are some interesting things that can come into play here. You can just roll this thing down the road and try to sort of understand the dissipation that's occurring within the tire. You can theoretically simulate things like skidding or cornering operations. All of these things are possible. You can look in detail at the sort of slip profiles over a contact patch. And by the way, another feature of contact problems we were talking about a little bit in our meeting earlier is that oftentimes if you've got an interface, you think of taking a tire, pressing it down into a roadway, and then rolling it. So the vast majority of that footprint is sticky. Right? It's not, and that's a good thing, right? Especially when it's snowing. But actually in a normal sort of steady state rolling operation, there's what's called a kick-out region. And so if this thing is rolling down the road, you'll have a highly localized band. This is just being pushed, it's not rolling, on one side that you actually want to resolve, because since it's slipping there, there's friction there, right? And so that has to do with energy dissipation, and it's something we'd like to understand. So these are the kinds of things that these guys think about. It's actually possible to couple them with system dynamics models. And so you can start to do some things also, like coupling a tire with a brake system, experiment with different control schemes for example, ABS type of braking, right? And then look at what that sort of makes happen in terms of the system dynamics. And so they can look at things like the clamping force that's necessary. Again, look at energy dissipation, which is going to relate directly to things like brake pad life, and in a manner that's completely coupled with what the tire is doing on the right through the dynamic system model. This gets at something I'm going to talk about at the very end of the talk. So fluid structure interaction. I know there's folks here actually in civil engineering who are doing important FSI work. Wind engineering has to think about that, right? So it's a very common example. But you actually see it in the tire business quite a bit too. And so folks would like to understand, if you drive through a puddle, for example, what is the loss of traction? Can we actually simulate that? One of the things these guys have done, if you think about, you've got a tire, you've got a roadway, and you've got intervening fluid. And because it's a contact problem, you don't actually know a priori at any instant, where the contact is going to be active, where the pressure in the fluid is actually going to be positive and it's actually helping to hold the tire up, and in what reasons you sort of got a free surface. None of this you know. You also, if you think about it for a minute, and you think of sort of in a Lagrangian meshing sort of way, really don't want to have to fix a grid on the fluid and have the grid deform with the fluid. It would actually be better, think about how we usually do CFD, if you could kind of take an Eulerian framework for the fluid and let the solid work through it, okay? And so there's some methods, and I'm going to talk a little bit later about how we actually do this, where you have the capability to roll this tire, for example, through a puddle. And it's not only, notice how this grid here for the fluid does not conform to the physical boundary. So there are ways to take care of those boundary conditions properly, and what they've also figured out how to do, you can't really see it very well here, but to adaptively regrid this region so that you get resolution of the dynamics that are happening there. So it's just sort of one example, but this is the kind of thing that folks are interested in being able to do. There's also the whole topic of particulate dynamics in contact, right? So in the tire industry, this could happen with snow, obviously. This could happen with gravel. And so here we've got contact between, a continuum mechanically described solid, but then effectively particle dynamics. And so having robust methods to do things like that is also of interest. Okay, so again, let me just sort of give sort of a wish list of things that we'd like to do here. Remembering we do numerical methods. So I'd like to be able to tell you something, if you're going to use my tool, about how accurate it is and how, at what rate, the error will reduce as you refine it. First of all, you'd like to know it's convergent, right? You'd like to know that if you use a finer grid, you'll get a closer answer. So we'd like to be able to tell you something about that accuracy. The robustness is something that I'll allude to in a couple of points, but maybe the way to keep in mind here, and let me just kind of turn this movie loose so you can see it. Keep in mind with all of these problems that we don't know a priori. We're going to put a boundary condition on this cylinder and sort of drag it across this rubber solid. But we don't know a priori. It's not a normal boundary condition, right? We don't know at any particular time where the contact is going to establish, where it's going to be free. We don't know where the interface might stick or where it might slip. We want the prediction tool to tell us that. The trouble is that it's out of contact, it's in contact. You'll see graphs in a minute. It's non-smooth, right? Most numerical methods, and I don't know how many of you in here do numerical methods, but think back to the first time you saw a finite difference method or something, right? We're always relying on something like a Taylor series expansion, one way or the other, to sort of derive a discrete method that we can use. So what do they tell you about Taylor series expansions? You're not supposed to apply them to things that aren't smooth, right? So this isn't smooth. This isn't smooth because I'm out of contact and I'm in contact. It also isn't smooth because I'm sticking and then I'm slipping, and it happens abruptly, right? So coming up with something that's robust, that's reasonably accurate, that we can use in 2 or 3 dimensions, all of those are sort of challenges, and I'm going to tell you a little bit about how we do it. So let me just give you an idea of what the equations are. Again, just sort of an intuitive idea of what we're talking about. And prior to the work that we did here, the way was usually taken to do these problems. And then I want to talk to you about mortar-based methods, which is what we've thought about for the last 10 or 15 years or so. And then, like I said, I'll give a couple of extensions to related problems at the end. So, we're interested in large deformations primarily. So, by and large, there will be some examples later that don't follow this formula. But by and large, we use Lagrangian methods, which basically means that your mesh that you put on the solid is going to deform with that solid in time. Okay? So we have some reference unloaded configuration, some current configuration. You can do this automatically, you can do it as a user specification, but the idea here is you want to pick out all of the points on the surface of either of these bodies and make sure that they don't interpenetrate the other body. That's sort of the idea in terms of impenetrability. And so you've got your usual equilibrium, F is equal to ma in continuum mechanical form. You can have displacement and force or traction boundary conditions, and we allow all of that. If you've got dynamics, you've got the appropriate initial conditions. But then you have to add these constraints, and these constraints are the ones that aren't smooth. Okay? So if we were to draw a picture of them, this first one is sort of the out of contact, in contact idea, right? So if you've studied, if you're an operations research person, or if you studied constrained optimization problems, one way to interpret mechanically what we're dealing with here is a classical Lagrange multiplier problem, right? So what happens with a Lagrange multiplier problem, you've got sort of a sine function. It's defined for each point on the surface of either of these bodies, or both. And we're going to define that function. Usually we define it so it's the distance between the point and the surface that it's opposing with a sign on it, okay? And the physical idea here is simply that that point has to stay outside the surface of the other body. It can't go in, okay? So that's the g less than or equal to 0. This Tn is, in mechanics, we call it the contact pressure. But mechanically, or I should say mathematically, that's the Lagrange multiplier that's going to enforce that constraint. Now, the thing that's a little bit different here, though, is this is a continuum mechanical description, right? So that Lagrange multiplier, at least in theory, could be defined for every point on the outside of either of those bodies. And we have to figure out the regions where we require a contact pressure to be developed to keep those things from interpenetrating, okay? So that's the idea. And then what we're going to do here, if you study plasticity theory for the friction law, is something quite similar to sort of a rigid plastic type of idealization. The only difference is that rather than having a yield stress like you'd have in rigid plasticity, sort of our yield stress, if you want, is going to be mu times the pressure, okay, which was here. So in other words, if that confining pressure gets bigger, then typically speaking with most interfaces, the sort of frictional yield stress, if you want to think about it that way, also increases. So we've got non-smoothness here, we've got non-smoothness here, and we have a different sort of variety of optimization techniques to try and sort of solve for those multipliers. So skipping a lot of details, if we take this system and we discretize it, which means we put a finite element mesh on it, you end up with a structural dynamics equation set that looks probably pretty familiar to most of you, right? So you've got your inertial terms. If we were dealing with a linear system, then F internal would just be K times D, okay? But it's basically the forces generated on the nodes by the stresses inside the bodies. We'll talk about this guy in a moment, and these are just your applied loads on the right, okay? So this would just sort of be your standard structural dynamics system. If you were doing structural dynamics in sort of a civil engineering sense, you might have a damping matrix times d dot in there too, right? But the sort of tricky guy for us is this contact force vector. And again, without getting into too much detail, those are the forces required on nodes to keep those bodies from interpenetrating with each other, okay? So the question is, we have very standard finite element recipes for how to go from, say, let me take the internal stress. So if I take, this, which is basically div sigma is equal to F, right? You can apply sort of a standard finite element recipe to come up with those internal forces in a finite element sense. What the Mortar method is going to be about eventually is how to do the same thing to turn these constraints, which are again pointwise fields over the surfaces of both bodies, how to convert those into what I'm calling FC here, okay? So it's a spatial discretization problem. And I'm going to kind of walk you through, how we figured out a way to do that that gives us some of these characteristics we said we wanted. Now, if I go back to the time when I was a graduate student, this is how everybody did contact, and the first contact algorithms I wrote looked like this. So, imagine you've got these two bodies, you've put grids on them, right? Now you're trying to decide, sort of heuristically, where do I enforce this constraint that nodes don't go inside the other body, right? Well, sort of a natural choice to make is just to pick all of the nodes on one side of the interface or the other side, or maybe both, and enforce that constraint in a discrete way, pointwise. Doesn't necessarily seem unreasonable, right? So a mathematician would call that a collocation approach. You've got some condition that you're wanting to enforce, and you have to pick a set of points where you're going to enforce it. Sort of the easiest way to do that is just to say, well, I'll do it at the nodes, right? It seems reasonable. Most of the algorithms we actually use for a lot of contact problems are based on it. It's actually not right. At least it's not right for the most challenging problems, and I'll sort of show you why that is. In fact, I've got a few quick examples right now that sort of give an idea of that. So this is actually out of my dissertation, so this is getting quite old at this point. So this is a 2D problem. This is an axisymmetric problem, and it's really just driving, so the axis of symmetry is here, and really all we're doing here is trying to drive a peg into a tapered hole, okay? Notice one other thing too, that both sides of this interface are deformable, right? So we said that these grids are going to sort of follow the solid as it deforms. So one of the problems here is if I'm going to pick either these nodes or these nodes and say, don't interpenetrate the other surface as we do the simulation, that surface, or that body that that node is looking at is faceted, right? And it's completely artificial. That faceting comes from the fact that I put a finite element grid on that solid, right? And you can actually see that faceting as you get bumps in the forces, right? So from a physical point of view, if you're sitting there on your computer screen with your coffee and you see this, you sort of feel good. You think, okay, well, it's at least enforcing the constraints. But, you know, we're usually interested in backing out things like what are the forces that are developed? Is it going to damage the surface? This kind of thing. And it's hard to make a lot of sense out of this. We certainly know it's not physical, right? So that gives us maybe at least some kind of clue that this collocation is not the right thing to do. I'm giving away part of my answer here, but about the time we started to work on this, people were thinking about problems of just joining grids, okay? Which, if you think about it, and I'm going to talk a little bit more about it in a second, is a really handy tool to have. If you've done any finite element method work, just as an analyst, right, you'll realize you may use a CAD tool to generate a grid for a piece, and you may use a different CAD tool or another description to generate a model for another piece, and those things are supposed to be glued together. It's a real pain in the neck, oftentimes, to make those grids match up, right? Your finite element textbooks will tell you the grids should match up. The convergence characteristics are only guaranteed if the grids are conforming, right? Well, who cares if they're not? Well, one reason you care, remember we said we wanted to be able to guarantee you a rate of convergence, right? So if you're using linear elements, you know, in other words, piecewise linear approximations of displacement, for example, then the theory tells you that the stresses should converge at order 1, right, as you refine the grid. And what happens is when you don't match up grids, you don't get that. It still converges, but you can actually see an obvious degradation in the rate of convergence. So remembering that we're going to have really fine scale stuff on the interfaces that we want to resolve, this is something if we can fix, we'd really like to. This particular example is one where there's sort of a boundary put in here and there was actually friction on it. But it's the same idea, whether I'm trying to glue that interface together or whether in the applications we're going to consider I want it to be free to slide, that degradation of convergence is a problem. So I'm going to actually take that mesh joining problem and use it to sort of describe our proposed solution. So the mortar finite element method, if you're not used to thinking about numerics, you can literally think about it, and where the name comes from is the mortar between bricks. So you imagine a brick wall, the bricks are your elements, and the question we're asking here is how do we design that mortar in a mathematical sense to give us some of these characteristics we said we wanted, the right convergence rate, and so forth and so on, and a little bit more robustness. So I'm going to consider the time problem first, where you just got, think of CAD Model 1, CAD Model 2, I want to glue them together. Forget about all the contact stuff, I just want to glue them together. Okay, how do I do it? And that's sort of the approach here. Now, by the way, I should go back to this. If I were to do the collocation approach, I would just take each one of these nodes on this interface and say, you can't move relative to that surface that you're sitting on. So you literally pin it there, okay? That has the problems we discussed before, right? You get less convergence, and in some cases you get non-physical results. So the question is there something else you can do? And what you end up with, you want, in a continuum mechanical sense, you want the displacements to match on either side of the interface. That's the idea of gluing those two models together. So we're going to introduce a Lagrange multiplier, and we're going to do that using an area integral. Okay? Now, for those of you who know a little bit about numerics, if we were going to do a collocation method, then there's the whole question of how are we going to approximate spatially that multiplier field, right? What I would do if I were doing a collocation method is it would be a sum over all the surface nodes of delta functions, right? Times nodal values. So what you do in a mortar method is you just use the same shape functions you're using for the displacement. It's kind of a natural choice, actually. It turns out to be right. And you use those to sort of expand, if you like, the approximation for the multiplier field over the surface. And you just plug it into the equations and you crank it out. And what you end up with is a set of nodal constraints, these CAs, but now they're little area integrals. And they're really tricky area integrals because they're inner products of shape functions on one surface with shape functions on the other surface. And this is why nobody did it, because it was such a nightmare to figure out how to evaluate these integrals. And I'll sort of give you an idea in a second as to why that is. Now, if I want to handle contact, and I'm just going to sort of obscure a lot of details in the interest of time. If I'm doing the tie-in problem, then I've just got a field. Once I solve this issue, I've just got a field of these force, it's basically a traction over the interface. If I want to admit contact, then all I need to do is take that traction, resolve it into a normal part and a tangential part, and then impose those constitutive models we talked about before. So the out of contact, in contact, in the normal direction, and then something here that, if you're familiar with plasticity theory, looks a lot like a slip condition, or a yield condition, I should say, in plasticity. So there's no particular point in dwelling on this too much once we've figured this out. The real point is how we're going to do those approximations of those inner products. So integral over the surface of shape function on one surface times a shape function under another surface. There's a problem there, right? If you know a little bit about finite elements, the underlying expansions describing those shape functions are different, right, for the two different bodies. You have to somehow resolve that. So what we do in 2D, it's actually not too much trouble. You sort of take this surface, so here's body 1, here's body 2. You parse it up into piecewise smooth pieces, and you can sort of go ahead and evaluate those integrals, sum over the interface. It's actually not too bad. In 3D, it's a bit of a nightmare. So now I'm kind of looking down on the contact surface. The red dots are sort of the surface nodes of one body. The black dots are the surface nodes of another body. And you can see pretty quickly that even for low-order elements, pressing on low-order elements, those sort of smooth regions, which I need to do those integrals properly, are polygonal. Okay, they can have 3, 5, 6. They can have any number of sides. So we actually, a few years ago, with Mike Puso out at Livermore, figured out a way to robustly do these integrals. And then another detail I'm not going to talk much about here. It's one thing to evaluate the integrals, but then remember, our global system of equations is nonlinear. We're going to use Newton-Raphson iteration of some sort to sort of get this thing to equilibrium. So I not only need to evaluate these integrals, but I also need to evaluate their derivatives with respect to the underlying displacement fields. So it is involved, but it is doable. And basically the idea is it better be worth it. Okay? So let me kind of recap where we are. So I still have yet to show you, although I've given you a little bit of evidence, that if I go to this trouble, and the folks from the domain decomposition community did this work for us a few years ago, they showed us that if you go ahead and enforce these constraints in this sort of way, you'll get back those rates of convergence we expect to get from the method. Now that's a pretty good deal, right? Because we're violating one of the basic rules of finite elements, which is we're not worried about the grid being compatible, and we can still recover the right rate of convergence. But it's painful, right? We have to do all of these silly integrals and linearize them and all that. But that was our original motivation for doing it, because I wanted to be able to tell you as a user, you're using this method, you're using whatever slip law you think is appropriate for the system you need to describe. There's a rate of convergence to it. There's accuracy in the tractions that you can expect out of it. All of that was our primary goal. turns out you get one other thing too, which we didn't really anticipate. And this is that the method is more robust. It actually enables you to take bigger load steps. It converges a little bit more easily. It smooths out a lot of the operators to the point where it actually works a little better. And I'll give you an example. I think this actually works. We'll see. So this is a really silly example, but it actually gives you the idea. I'll run that again in a second. The idea here is I'm going to take this red block, I'm going to push it down into the base block, and I'm just going to try to move it tangentially. Now, think about what's going to happen. If I do sort of the old node collocation approach method, those nodes kind of fall off of cliffs, right? So I push it down, I develop a very high nodal force to prevent the interpenetration at each one of those nodes. But then as I move this thing progressively closer to the edge, at some point, these nodes leap off the edge, that force goes to zero, and the Newton-Raphson method just can't converge it, right? The point is that with a mortar, which I'm showing you here on the left, it smooths those operators because the constraints are non-local, right? They're evaluated over those sort of funny polygonal areas that I showed you before. So it smooths the operators. And so there are a lot of problems like this, particularly for deformable to deformable contact problems, where you sort of can't get these traditional methods to even work, okay? And because of the smoothing here, so you know, that's the sort of unexpected bonus we got here was the robustness. And so this is Bin Yang's work, who was one of my PhD students a few years ago. The one on the right is dynamic. The one on the right, the one on the left is dynamic. The one on the right, which I apologize for the quality of this, is actually a crumpling cylinder. Okay, so in this particular case, this is the kind of thing that folks who are doing crumple design at Ford and places like this are interested in. You actually, an important dissipation energy mechanism is to be able to crumple these things. So we like to be able to simulate that, and you've got contacts happening throughout. So we were able to sort of show that not only did this method give you more robustness, but that it was pretty generally applicable. And another Michelin toy problem, which actually got Ben his first job, because he went to Abacus and he showed this very movement. And they knew that none of their versions of Abacus could do this problem, and they offered him a job. Right? So it's good sometimes if you're a graduate student to have that killer app that you can show somebody. It doesn't look like very much now, but it was a big deal then. The idea here is this is actually a run flat tire, which was all the rage for a while. And if you know anything about run flat tires, you know the failure mechanism is basically on the inside of the tire. They put a lubricant in there so that the thing can run flat for some distance, but at some point that lubricant gets hot enough that it starts melting the rubber, right? So the idea is they just wanted to understand, again, those dissipation mechanisms well. So it's a pretty cool method, right? It is not the tool for all problems because it is expensive. You know, doing all of those area integrals that I showed you earlier, it's an involved analysis. It's much more heavily coupled across the interface than traditional methods. But oftentimes it's the difference between being able to do the problem and not, okay, because of the robustness. And we didn't really guess the robustness. That was something we found out with time. So what I sort of promised to do in the end is to show how some of these ideas are interesting in terms of extending them to other applications that involve either different types of contact or fluid structure interaction. So this was actually work that we were doing for Sandia a few years ago with a colleague of mine, John Dalbo, who works on extended finite element methods, and I'll tell you a little bit more about what those are in a moment. But what the Sandia guys wanted to do is look at crystalline microstructures, and what they were curious of, or curious about, is there a way to take a topology like this, and this is 2D, so 3D is much harder. Again, you do what your finite element textbook tells you you need to do, your grid should be compatible across grain boundaries, right? That's maybe impractical in 2D and it's almost impossible in 3D. And just to give you another level of complication for this, these guys wanted to do stochastic methods. So they wanted to be able to do these simulations thousands of times in sort of a Monte Carlo sense. So they really didn't want to do this. They didn't want to have to generate these grids that over each grain boundary matched up. What they were interested in is, can I give a grid like this, which pays no respect whatsoever to grain boundaries, and this is sort of what extended finite element methods are designed to do, and give me a reasonable answer. Okay? And I'm going to go a little bit quickly here so I don't run out of time, but we were also involved with some energy harvesting work, which leads to the FSI stuff I'll show at the end, that had us interested in this as well. So the idea here is, how do we take, let me give you just an idea of the equation. So suppose I've got two grains. I've told you now that I'm going to try to figure out a way that I don't have to put element boundaries exactly on that interface, that they can kind of pass through somewhat arbitrarily. So really what we do here, you do what the XFEM people call enrich the displacement field, okay? And what this really means, and I think I've got a picture here that shows this pretty well, is you build in the possibility for jumps in the displacement field as you cross a grain boundary, okay? So this is not a finite element method anymore. It's what we would call an enriched or an enhanced or an extended finite element method. And you use these sort of spatial Heaviside functions to do it. So skipping a lot of details, what we're going to be after here is using methods like this to allow these grain boundaries, if you like, to come apart. And then we're going to put the Lagrange multipliers back in. Remember the tying problem, right? To sort of enforce compatibility, or if we want to let it slide, we can let it slide. Okay, so your sort of first naive impression would be, well, let's use the trick that worked when we were doing contact problems, which is we just use the displacement shape functions to describe those multipliers. That is a disaster. And I'm going to skip the equations and just show you what you get. So this is a simple beam bending problem. This is a numerical oscillation, right? So these are literally the multipliers on this interface as you move along it. And basically what we would say here is this is not a stable approximation, okay? It turns out, though, that it's pretty easy to fix. And the idea here behind stabilizing this multiplier field is simply to put in more displacement degrees of freedom, or what are called bubbles, okay? And if you studied finite element methods a little bit, in fact this comes up in incompressibility as well, you have something called the LBB condition. And basically that condition says that when you have a mixed problem, in this case between pressures and displacements, there's sort of an inequality that needs to be obeyed between the number of displacement degrees of freedom, roughly speaking, and the number of pressure degrees of freedom. And if that gets too different from what's happening in the underlying medium, you get the sort of oscillations we saw a couple of slides ago. So this is a pretty standard stabilization method, and it actually works. And it also gives you the proper rate of convergence. And so what people have actually been doing for quite some time now is using these sort of, they're related to mortar methods, but you have to enrich the displacement field to actually give the analyst flexibility to not have to grid all these grain boundaries. So this is a pretty attractive method. And again, you see the unstable result on the upper left, and then you see the stabilized result on the upper right. Okay? And finally, I'll just sort of conclude with fluid structure interaction. Similar sort of motivation, different XFEM. But the way you want to think about this here is, suppose I've got, I don't know, think of a bathtub. I've got a deforming, squishy thing that I'm going to use a Lagrangian solid for. That can be this blob B, floating in a pool of water, okay? And the idea here is I'd like to use an Eulerian grid for the water, kind of like I was talking about in the beginning with the tire going through a puddle. and I want to use a Lagrangian grid here, that's going to give me compatible grids on that fluid structure interface as well. And so we've had some success in recent years in applying these principles here. You can sort of look at simple, vortex shedding examples to see the effectiveness of the method. Jessica Sanders, who actually did this work with me and then ended up going out to Livermore to work with Mike Puso and some of their production codes, they were able to show as both fluid mechanics and solid mechanics applications that these same ideas of stabilization not only worked quite well, but they could be generalized to large deformations as well. And they're really discontinuous Galerkin methods, which I won't get into here, but it's really the same principle that we've been discussing that makes those go. So, just to sort of summarize my story, and it's pretty well done, and if we've got time, I'll take any questions people might have. Probably not surprisingly, it's oftentimes is true in science that we sort of look back and go, well, that should have been obvious, right? So finite element methods are predicated on the idea of taking the governing equations and weighting them in a variational way over volumes of material, right? It probably shouldn't be a surprise that we should do the same thing with interface mechanics, right? Which is effectively what we're doing here, okay? But sort of the nice surprise is the right thing to do, it gives you the convergence you should get, blah, blah, blah. But it also really has this nice benefit in large deformation problems of giving you quite a bit more robustness. If you've ever had the experience as an analyst of running a nonlinear finite element code and doing contact, you'll know how frustrating it is. Because this sort of non-smoothness bites you all the time, right? So the smoothing that these operators give you is really attractive. And then the other thing we've learned, and that I tried to show rather quickly at the end, is if you extend these to XFEM and embedded interfaces, you can do it, but you can't do it in a naive way. There has to be a notion of stabilization there. And I think this is really an active area of work now. There are a lot of folks that are really thinking about FSI in a different way, and the methods that they're using to do that, at least in the finite element world, are quite closely related to these Morter methods that I sort of started my talk with. So with that, hopefully I was more or less on time.
Thank you very much.
Thank you.
So now, any questions for Professor Lerch? Yes, Shiva?
One thing a concern is about the well-postness of the original problem.
Yeah.
With the linear moment imbalance and the contact constraints. With rigid contact, there are issues of well-postness.
Yeah.
So when
With Coulomb too.
When a simulation doesn't work, I wonder, are we solving a poorly posed problem, or is that a nice one?
Right. So, yeah, he's right. So he's asking the question, if the original continuum mechanical problem is not well posed, maybe one way of interpreting your question is, how is that going to show up here, and how will we know
Right.
that if we have a problem, it's so it's pretty heuristic. I sort of have to admit that. The most serious well-posedness problems are actually in Coulomb friction, and if you go back to the work that Kikuchi and Odin did in the 80s, they give you a number of examples of, actually to be rigorously correct, to even take a Coulomb friction law, which by the way never works, but we insist as engineers of using it, right? So physics be damned, we still use Coulomb, right? It also has mathematical problems, and they're pretty well documented. So that chance is already always out there, right? The kind of numerical difficulties, though, that I'm talking about here are not they're ones where if we apply a discretization method or a different scheme or whatever, we can get an answer, okay? The cases where I was showing convergence, there is a known solution that we're sort of evaluating convergence to. So in that sense, it's a little bit rigged. these lack of uniqueness issues, and that's really what tends to come up quite often with Coulomb friction though, are recognized. We don't actually see them too much in practice, but it's always a possibility. And there are pathological cases. I think, just to give you one, which I think you'd know from your own work, is if you're talking about dynamical systems, particularly that have the opportunity to bifurcate, then it becomes very difficult to know whether the difficulties that you're seeing are actually something that's real, something that's in the governing equations, or something that is introduced with your approximation. So it's always there, but at least the applications I've showed here, there's reasonable evidence to suggest that the problems are well posed, at least. Yeah.
Yeah, so for the contact problem, I'm just curious if has somebody used spline-based description of surfaces
Yes.
to resolve contact points and contact pressure?
We did this. Yeah, we did this. In fact, we did it before we did mortar.
Okay.
And we were trying, and our motivation purely was to spatially smooth the operators. And it actually works, but it still has the accuracy problems. And in effect, it's even worse because it's hard to prove theorems when you sort of take the finite element discretization and you say, I'm going to approximate that in the contact operator with a spline, right? You can do it, and actually, in terms of robustness, it works quite well. I did some work with Mike Puzo 2 or 3 years prior to this, and that's exactly what we did. But you can't really prove theorems about it. So you don't typically know how much accuracy you're getting. That's the downfall. But if you look in most of the production level codes that are out there, it's got contact smoothing in it, and it is a popular method.
So the physical problem often is multi-scale, because contact is actually through asperities.
Yep.
And so I wonder, you've done a lot of applications, have you encountered situations where that became important, and how would you go about trying to solve them?
We have, and I don't think we've solved them very well. I mean, the work that I've seen that's probably closest to this is folks who are looking at these sort of hybrid approaches where you take atomistic simulation somehow and you couple it in. We haven't done that ourselves. I think there probably is some wisdom buried in this about how that coupling could be done, spatially to be numerically robust. It's a good idea, but it's not something we've really had the chance at least to pursue in our work. But yeah, the whole multi-scale, I think there's sort of 2 areas for improvement, let's put it this way. One is multi-scale. The other, which there are heuristic methods in production codes that you can use, is adaptivity. Because you sort of know that on the fly you'd like to have that, right? That's an area I think that improvements can be made.
Any other questions?
I have a question, this is tangentially related. So you analyze the tire, so my interest is my tires don't last more than 60,000 miles.
Right.
So how do you degrade the tire?
Well, so a few answers to that. If you're in steady state rolling, which you're not, of course, right? So the 0th order answer to that is non-steady state rolling, right? Cornering operations, accelerating, speeding, slowing down, all of those introduce areas of slip on the tire, which of course is what a skid is about. But in a normal turn, you get that as well. So on the surface of the tire, there's any time there's slip, there's dissipation, and there's at least the potential over time, to accumulate damage. But even in steady state rolling, as I mentioned sort of in passing, there is that highly localized region where slip occurs, and they call it the kick-out region. And it's very hard to resolve. It really, you would want a multi-scale approach, right, to do it. But then I think the other thing that's actually kind of interesting to think about, and tire designers do this all the time, is there's always trade-offs between, say, the geometry of the sipes and grooves and things like noise, right? So if you're trying to minimize noise, that's going to give you a different tread design than, say, is going to give you dissipation inside the tire below a certain level. You see what I'm getting at? So they're having to make compromises like this all the time, and it's complicated, but that would be sort of my first order answer. The other one, of course, and maybe this is more applicable to truck tires than passenger tires, but you just have to look at the carcasses by the freeway to realize that there's stuff going on inside, right? Between that sort of sculpture of the tire and the bands underneath, and there's dissipation that occurs there too. And in truck tires, that delamination is usually why we see those pieces of tire by the side of the road. So there's a few things in it.
Yes, you have a question?
In the example of the flat tire, where the damage is faster than the degradation of the surface, how do you simulate that damaging the material in the flat tire?
I'm sorry, I didn't quite get, how did I simulate which in the run flat
In
tire?
the flat tire,
Yeah?
you were simulating the degradation of the material because of the gel, right, that gets it?
Not really the degradation, just the dissipation, right? So, again, this is sort of one of these heavily heuristic areas, but if you were to take sort of the product of the frictional stress and the slip velocity, that gives you a dissipation, right? And then if you integrate that over a tire or over a surface, that gives you an idea at any instant in time how much thermal energy is being generated. You know, so that was basically the calculation we were doing. The next obvious step, which I think maybe is the question you're asking, you might want to put a damage model in there or something. We weren't trying to model the damage. We were just trying to quantify, you know, what that dissipation looked like and where it was happening. Does that make sense?
On damage, so she can work with you on damage.
Yeah. I mean, I think we're sort of to the point where it could be credibly done, right? I mean, think about it this way, for those of you who model things like damage. You know, when we entered this field 30 or 40 years ago, all you had was these sets of discrete Lagrange multipliers on an interface, and you know, where do you even start in coming up with an approximation of damage models? Need to involve things like slip velocity and pressure and frictional traction and maybe history variables. And there just wasn't even a kinematic framework to think about those kinds of things. So I think now that we have some of that a little bit more established, and it turns out to be the right thing to do numerically, there's a little more hope for doing things like that than there once was.
Yeah, we just calculate the entropy generation in the system to the damage.
Right.
But you have to calculate it for all the mechanisms because there are multiple mechanisms.
Right.
And which is not easy.
Right.
Any other questions? Okay, thank you very much.
Thank you.